related to the topic of the workshop, to a more general audience. So we're very pleased today to have Tom Mrowka from MIT, who will talk about an approach to the four-color theorem using gauge theory and three-dimensional topology.
That's always, in spite of what it says there. Yeah. Anyway, so it's always a pleasure to come down here to Stony Brook and come to the Simon Center. This is, as strangely, almost everything I do is joint work with Peter Kronheimer. Both of us, sadly, at the moment, are running our respective departments, which makes mathematics go very slowly. But anyway, I'll tell you what we've been thinking about. So we've been thinking about the four-color theorem. That was not our plan, by the way. Our plan was to just do our own thing. But then, anyway, it turns out we were thinking about the four-color theorem unbeknownst to us. So the this is the four-color map theorem proved by Appel and Haken in 1976, 50 years ago. 40, yeah, sorry. Whatever. 50 sounds better. Anyway, something like that. So every planar graph admits a four-coloring of its complementary regions. So, of course, the original proof, only kind of proof that's known today is computer-aided. That was a big, quite controversial when it first came out, and their 1976 proof was simplified quite substantially. I don't remember exactly the numbers, but Appel and Haken's proof reduced it to checking that certain, some 2,000 some odd graphs you had to exclude. What? I don't think so. I think it was like 2,000, except that they're not so small. I mean, it's, anyway, it took back then thousands of hours. In 1995, Roberts, Sanders, Seymours, and Thomas simplified the proof quite a bit, but it's still something like 600 or 700 cases that had to be checked, and still that was still a lot of computer time. And then my talk ends ignominiously. That's not very good. What happened? Sorry, we'll have to see. Why did that do that? There's a lot more talk here. Or maybe for some reason there are a bunch of blank pages. Okay, I should have just been confident and kept going. No? All right, let's see. If I start here. Okay, sorry. It's going to be a smaller looking talk. We'll just do it from here. Okay, so I want to explain to you a kind of very old reduction of the four-color theorem. So a Tate coloring. So I'm going to be working in the context of trivalent graphs always. So one easy thing to do is to see that actually you might as well do the trivalent case. If you know the trivalent case, you can easily reduce the general case to the trivalent case. So we're going to look at trivalent graphs. And what we want to look at about trivalent graphs is notion of what's called a Tate coloring. So that's a three coloring of the edges. So that the three edges meeting at any vertex have different colors. So here's the dodecahedron as a planar graph. The one skeleton of dodecahedron is a planar graph. And here's a three coloring of it, Tate coloring of it. Okay? So I hope you can see that. So at each vertex, the three colors are always different. Okay? Sorry. I think I forgot one thing. Oh, all right. Sorry. We're having some more technical issues than usually I have. Okay, I have to. So the four-color theorem is equivalent to the statement that all. I have to tell you what bridgeless planar trivalent graphs admit a Tate coloring. Okay, when a graph is called bridgeless if there's no edge that I can remove that separates it. Okay, why is that relevant to the four-color theorem? Well, if I have an honest map, no country has a border with itself. Having a border with itself is equivalent to the statement that the boundary graph has a bridge. Okay, so and anyway, it's equivalent to the fact. And if you have a bridge, then you don't have a coloring typically. So I have no idea. I don't know any graph theory literature at all. Okay, but so the four-color theorem is equivalent to the statement that all. So, and I just want to. This is a pretty little argument, so I just want to. It being a colloquium sort of thing. Ooh. We're going to go to yet a different program. Sorry. I'm just going to show you the tech thing because none of my stuff is coming up. All right. Does this have? All right. So, sorry. See? There was the definition of bridgeless. That's got a bridge. See? It's called a bridge. Proper map, great. Oh, look at that. That's nice, isn't it? I know what happened. I changed the file. Sorry, I'm just bear with me. I'm just going to try opening this guy up again. Shoot. No, not that one. Sorry. Let's see. Yes. Okay. Let's try to go to full screen again. View. Yeah, we're getting there. All right. There we go. Wonderful. Okay. So here's the idea. I'm going to explain how you go from knowing this three coloring to four coloring the complement. Okay. We're going to color the outside of it white. Every time we cross an edge, so when we go from a white region, we're going to keep the color of the edge to color the next region. And then, if this guy's blue, then if I go across blue, I'll go back to white. If I go across green, I'm going to go to red. If I go across red, I'm going to go to green. And it's because of this. So that's the result. And that's a consistent rule. Well, because the three colorings are different at the vertex. And in fact, what's going on? Okay, so let's make a definition that'll be important for the rest of the talk. So let's call Tate of Gamma. That's the number of colorings, number of Tate colorings of our graph. Okay, the permutations of the colors are going to be distinct. There's two combinatorial characterizations that'll come up later in the talk. So really, you can think a good way to think about what we're doing when we're doing this coloring is that really what we're doing is we're coloring the edges with non-trivial elements of the Klein-4 group. And we're using the multiplication in the Klein-4 group so that the property that the three vertices, the three edges coming into a given vertex are distinct translates here to the fact that the product of the three elements is 1. Right? Three non-trivial elements is 1. Well, all of the elements too, but that's not so interesting. Okay, so a Tate coloring then gives an assignment to each edge of our graph, a non-trivial element, non-unit element of the Klein-4 group, and then with the property that the elements for the three edges incident to a vertex are 0. This is also called a Nonzero V 4 flow in the graph theory literature. Okay, I know a little bit. of graph theory literature. Okay, now, if the graph has a planar embedding, then we can reinterpret this in a way that we can start to like, actually. We can reinterpret this as a representation of the fundamental group of the complement of the graph. So a representation of the fundamental group of the complement with the property that into the Klein 4 group with the property that there's some distinguished generators. There's a distinguished generator. We imagine the north, up at infinity, there's our base point, and then for each edge, there's a generator. And what we've done is, so then we send that generator to the element that the edge was assigned. Okay, so just simply the question of existence. So by the way, it's easy to understand if I was just looking at representations without this property that I want each of these distinguished generators to go to something non-trivial, that's just homological, boring. But it's this extra property that I want each these distinguished generators to go to something non-trivial that makes it an interesting problem. But now that I've changed this into a problem about representations of the fundamental group of the complement of my graph, I can think about this just more generally. I don't need the graph necessarily to be planar. I don't need it to be just in the 3-sphere. I could think of it in any 3-manifold. And that is what I will do. There's another little nice little thing to notice. I want to change this into a problem about 3-manifold topology and gauge theory. So a few little reductions that we're going to do to get there. So of course, each element of the Klein 4 group has square 1. So the representation, well, we had a representation of the whole fundamental group into the Klein 4 group. It descends to a representation of the fundamental group where we kill the square of each of these distinguished generators. Right. So good. Okay. Now we're in a context where there's actually a fair amount of literature, some of it in the physics literature, some of it in the knot theory literature. So there's a notion of a web. So a web for us is a pair, a 3-manifold and gamma. So gamma is a trivalent graph, which we think of as being embedded in our 3-manifold. And okay, there's the most boring non-trivial web, the unknot. There's another web. A knot is an example of a web. And here's another example, so that the whole picture somehow can be knotted, and that's part of the story. I've drawn it thickened so you can see it better, but you should think of this really as a graph. Right? This is not not a genus 2 surface. It's a graph. Okay, but okay. So the next step in trying to make this into a more geometric problem is to notice that actually a web in a natural way gives rise to an orbifold. So the way to think about that is the following. So I look at R3, and I think of the action of the natural action of the Klein 4 group, where you think of the Klein 4 group as the orientation preserving diagonal matrices, right? And if you take the quotient of R3 by the Klein 4 group, what you get is homeomorphic still to R3. So if I took just to see that, I mean, there are a lot of different ways to see that. Maybe the simplest way to think about it is the following: if I took the action by all diagonal matrices, I can put everything in the first octant, right? And so if I quotient instead by the Klein 4 group, so half of the diagonal plus minus 1 matrices. What I get is the quotient space is 2 copies of that octant identified along their boundary. In other words, R3. But it's not just it's not as a smooth manifold. It's not R3. The 3 coordinate axes each get folded over under that action. So the quotient naturally has, as a singular locus, is y, the basic thing that we want for our trivalent graph. So if we see a trivalent graph, we can kind of think that that's supposed to be the singular locus for a kind of rather simple orbifold. The point stabilizer along the edges is Z2. The point stabilizer of a point at the vertex is Z2 times Z2. Okay? So that's what we're going to do. Orbifoldication. Okay, yeah, anyway, so that's said slightly differently. Yeah, there's orbifoldication. Good. So given this web, we can construct an orbifold. And this orbifold had the nice property that actually it enforces this quotient of the fundamental group that we wanted. Right? So what we can do, if you have an orbifold, right, so think of an edge. An edge in the graph. The picture of the corresponding orbifold is that it looks sort of like this has a cone-like singularity times r, two-dimensional cone, and it has in the world, orbifolds have a fundamental group, and in the orbifold world, the fundamental group, a loop that goes twice around this cone point is contractible. A loop that goes once is not. So that kind of imposes this relation in a geometric way. Yeah. Okay. Okay. So the orbifold fundamental group is this quotient that our representation lives on. So here's at the moment you should think of this as a ridiculously fancy way of restating the 4-color problem. So a coloring of a planar graph exists if and only if there's a representation of this orbifold fundamental group so that these edge generators have non-trivial image. A slightly nicer restatement, I mean, again, it's sort of trivial, but a slightly nicer restatement is that if, so to each planar graph, you should be able to associate at least one 3-manifold with a Klein-4 group action so that the quotient of that 3-manifold by the Klein-4 group is this orbifold. So it's sort of, there's not all orbifolds are quotients. And the 4-color theorem says that if I have a planar graph, then actually that's a quotient orbifold. Again, that's a completely, if you're a graph theorist, you should just still be annoyed. Okay? But I haven't told you anything really interesting yet. But I hope that I will convince you that there are interesting things to say. Okay. Well, so I don't like to do gauge theory for the Klein-4 group. We had a discussion at lunch about whether that is properly even a Lie group. Anyway, in any case, let's look instead at we're going to look instead at representations into SO3. So we're going to look at the representation variety of so homomorphisms from the orbifold fundamental group into SO3. Think about that for a bit, and of course, there's an action by conjugation on this thing. And then there's the representation variety is usually equivalence classes by conjugation. Anyway, so that's our guy. Yeah. Okay. So, this our gamma we can think of more more gauge theoretically as being equivalence classes, isomorphism classes of pairs of principal orbifold bundle and a orbifold flat connection. Yeah. So actually, the condition, this condition, that the edge elements go to are non-trivial, is natural in the story. It's helping you pin down which orbifold SO3 bundle you look at. There's a topological classification of them that you have to understand, and it turns out that at least if the graph is connected, this condition pins down. There's one isomorphism class corresponding to that condition. So I want to digress for just a tiny second about representations into SO3. So these subgroups of SO3 are the possible stabilizers of a representation. So they're these are the groups that can be the normalizer of another group. And there are also, this guy's its own normalizer. Both of these are their own normalizer. These two normalize each other, and these are the identity and SO3 normalize each other. Okay. Yeah, so the first little observation. So when we do gauge theory, we like to stay away from things that have stabilizers. Well, we mathematicians, I should say. The physicists don't care. It's okay. And anyway, so if if we have a vertex, then any representation, well, it already, if there's a vertex, then it already fills up. That vertex tells you it fills up the Klein 4 group already. So you can't have O2 as a stabilizer in that case. So it'll be important to understand what we want to understand. Yes.
There are lots of other subgroups.
Yeah, but they're not normalizers of other subgroups. Not
ABE discrete groups.
Then they typically have trivial normalizer. And nothing commutes with all of the elements. Right? Yeah. Yeah, I mean, of course, there are lots of interesting subgroups of SO3, but these are the ones that, are normalizers of other subgroups. So one thing that's going to be important in the story, we're going to try and understand actually the based representation variety. And the reason these subgroups are important is because if I have a representation with a given kind of stabilizer, then its orbit under conjugation is the quotient of SO3 by that stabilizer. And here are the possible kind of, so if the stabilizer is O2, I get an RP2. If the stabilizer is V4, I get the three-dimensional flag manifold. If it's Z2, then I get a certain lens space. And of course, if it's trivial, then it's RP3. That'll be important in a second. So why is it important? So let's look at what happens if I look at some examples of graphs. What is this based representation variety? So the simplest one is the unknot. The unknot, well, it has no vertices. Its stabilizer is the image of the representation is just Z2. We require it to be non-trivial, and so the based representation varieties are RP3. Well, there are three Tate colorings. The rank of the homology, RP2. The rank of the homology of RP2 is 3. Now we're sure we're onto something. If I look at the theta graph, its based representation variety is the flag manifold. The number of Tate colorings of this guy is 6. And the rank of the homology, Z2 homology of the representation variety is 6. We feel even more confident. Now, we look at the trefoil. Its representation variety actually has 2 components. Well, actually, this is telling you that the invariant actually depends. It's not an invariant of the graph. It's an invariant of the embedded graph. So there's something interesting going on here. The rank of this homology group is bigger, and it doesn't, not surprisingly, it doesn't have so much to do with the Tate colorings anymore. It's just noticing some richer information. If I look at the cube, so that is the one skeleton of a cube as a planar think of it, it's a trivalent graph. Its representation variety actually is a mess. The 24 Tate colorings, and well, this thing, I mean, you could compute it. It has nothing to do with anything. Just the homology of that thing has nothing to do with anything interesting at the moment. But of course, we're used to this kind of thing. This thing is singular. It's not a manifold, actually, even. But we know what to do. We're trying to do instanton gauge. We're going to try and do instanton gauge theory. We're going to perturb things and see what happens. Yeah. Okay, so yeah, anyway. So now we're going to, this is the slide in which you actually start to do gauge theory. So we're going to fix an orbifold bundle with the property all the point stabilizers act faithfully. So there's only one isomorphism class, and we're going to do gauge theory on this bundle P. So we're going to look at the space of gauge equivalence classes. So if the graph is in S3, which usually it will be for the talk, I'm going to eliminate the 3 manifold from the discussion, but from the notation. Okay, so orbital connections. And so there's a Chern-Simons function on this space. I won't tell you what my normalization is, but it has values in some circle. And the great thing about the Chern-Simons function is that its critical points are flat connections. The gauge equivalence classes of flat connections. And so so the critical set we can identify with this thing that we want. And now you're if you haven't seen this before, the game is we're going to try and do the Morse homology for this function or one form. There's some tricky business there because it's actually multi-valued. I mean, as a function, it's multi-valued. It's circle-valued function. But this picture already tells you, maybe it gives you some hint about what you're supposed to do with the cube. Right? The cube is singular, but if I could think of trying to perturb the Chern-Simons function to make it regular, and that's what we'll do. So anyway, we want to do Morse homology for Chern-Simons. There's a little technical point. It's a colloquium. We'll sort of skip it, but there's some little technical point about the critical points of Chern-Simons are conjugacy classes, identify the conjugacy classes of representations. We actually want the based representations, not conjugacy classes. There's a little trick for dealing with that by introducing an extra copy of the theta graph disjoint from our graph and doing gauge theory there. So there's a slightly, by modifying our graph, we can make the critical point set be exactly the based representation variety of the graph.
Does it matter if it's actually linked or not?
Yeah, it does matter. And it's not. It's just the theta graph is off somewhere, sitting calmly undisturbed by the rest of the story. So think of it like a gauge theoretic base point, right? Which, as we know from algebraic topology, we have to remember. Otherwise, we are wrong. And, anyway, so at the end of a very long day, we're only going to do this with Z2 coefficients. Actually, there's a very interesting story about whether you can do this with other coefficient groups. You can't do much better than Z2 for more subtle reasons than usual, but there's a vector space we can define the Z2 Morse homology of the Chern-Simons function, and that gives us an invariant of graphs.
So there's some orientation issue?
No, actually, it's more interesting than that. So it has to do with, because you can have bubbling at the vertices, there's you can only do Z4 at best, even if you can do orientations. So anyway, okay. So I want to. So we have it. So just to summarize, for each graph actually embedded in each trivalent graph embedded in any 3 manifold, once I take care of this base point issue, I have an invariant which is a Z2 vector space. Okay, so I want to have I need, bridgelessness was important in the planar case, and it turns out also to be important in the study of this invariant, but we need a generalization of bridgelessness to handle embedded graphs. So now it's going to be a property of actually the embedding. Sorry. This is supposed to, well, okay. Actually, in our paper, we call this spatially bridgeless, so I should have edited this to say spatially bridgeless. I will say spatially bridgeless from now on. So a web is called spatially bridgeless if there's no embedded two-sphere in the three-manifold which meets the graph transversely in one point. Okay, so here's the same graph, but with two different embeddings. In this one, it's, the graph has a bridge, no matter how you look at it. This embedding, spatially, it still has a bridge. With this embedding, it's spatially bridgeless. There's no two-sphere that hits the graph just in one point, transversely. Right? Even though the graph has a bridge. So it's spatially bridgeless, the property of the pair and the embedding. Okay, and this is sort of a generalization of prime, or irreducible for three manifolds. Yeah. Okay. Good. So the basic structural theorem that we know is that actually, if again, I should say spatially, if this is a spatially bridgeless web, this could be any three manifold, but then the rank of this homology group is non-zero. Okay, that's nice. And the idea is that for this proof, borrow from our earlier work where we proved property P. So we proved, Peter and I have proved quite a few theorems on guaranteeing that three-manifold fundamental groups have non-trivial representations into SU2. And these, in turn, our work is based on some work in other kinds of Floer homologies due to Juhas, Ni, and Gigini, and then eventually goes back to Gabai's work on sutured manifolds, and so somehow there's a very interesting interplay between this theory, Gabai's theory of sutured manifolds, and these gauge theoretic invariants. They are sensitive to this structure, and it's quite nice that in fact, in some sense, Gabai's work goes back to Hawkins' work. So, maybe he knew something else. Anyway, and just to mention, the way spatial bridgelessness is used is to verify that a certain sutured manifold that we construct is taut. So taut is important. If you're in that world, you understand that taut sutured manifolds are where it's at. Okay, so the main conjecture is that actually the rank of this invariant, so remember that we have the rank of J sharp of gamma is actually equal, if it's planar, if I have a planar web, then it's equal to the number of Tate colorings. Okay, so
does a planar graph always minimize the minimum? Right?
Does a planar graph always minimize the?
Take an abstract graph and look at all its embedding.
Yeah, we don't know. That's a reasonable thing to believe, and that I don't know if that's hard to prove. Actually, we thought about it. We haven't actually thought about trying to prove it. Okay, the conjecture, of course, it implies the four-color theorem because, well, we already know that for a bridgeless planar graph, this group is non-zero, and then that tells you the number of Tate colorings is non-zero. That proves the four-color theorem. I want to emphasize it's very different. They're actually there's a raft of reformulations of the four-color theorem. They're all actually completely equivalent to the four-color theorem, and they don't somehow, what they change them into problems that look algebraic. It's a very beautiful. They're all based. Penrose has this beautiful paper, which eventually all these other things are based on, but you can translate the four-color problem, I mean, in this, it's still translated in exactly the same way into this Tate coloring problem, into a problem where some complicated algebraic expression is non-zero. But you have no idea why it should be non-zero. Just, you know, it's sort of, so to say, there are interesting ways, you can write down interesting formulas for this Tate number, the number of Tate colorings. And some of those interesting ways look very algebraic, but you have no idea why it should be non-zero. So anyway, that's good. So what I want to explain in the rest of my talk is that actually this isn't just an inert group. It has a lot of structure, and hopefully that structure will eventually help us either, you know, at least put us out of our misery. We've got to know what's the rank of that group, right? Because maybe we win, maybe we don't. But we do know many things. So what I want to explain is that actually there's a functoriality property. So there's a natural generalization of webs to the four-dimensional case called foams. Well, actually to any dimension, but it only seems interesting to us in 3 and 4 dimensions. There's a large literature on this. So let me show you some pictures of what a foam looks like. So here's some elementary foams. A foam is something like a two-dimensional web, except that now the colors and the arrows are not important for our story. They were important for their story. Okay, so they're there. This is from paper from McCase, Thuschitz, and Vaz. A foam is a two-complex with the property that if I cut it, there's some one-dimensional edges, and those one-dimensional edges, 3 pieces of surface can come in. Exactly 3. That's it. So here's a few pictures there. And there can also be some singularities at a vertex. At the vertex, there can be 6 two-dimensional faces that whose closure include that vertex. So anyway, in the literature, sometimes what I'm calling a foam would be called a prefoam, but I'm just going to call it a foam for my purposes. So what I want to explain is actually those pictures that I just showed you. They're the natural generalization of what I already did. I wanted to make an orbifold out of this web. Well, I want to have something that I can make an orbifold out of that's two-dimensional. So what I do is I take the order 8 subgroup of SO4 consisting of diagonal matrices. So the orientation preserving diagonal matrices. Oops. And again, same argument tells you that the quotient spaces are 4, right? Because if I quotient by all plus minus 1 diagonal matrices, I'd get an orthant, and it's 2 copies of the orthant, so it's R4. Now, the 6 coordinate 2 planes, they get quotiented out to give me half planes, but kind of singular half planes. 1, 2, 3, 4, 5, 6. Yeah. So that's the picture that you saw in the web literature, foam literature rather. And just so another way to say what the cone point, another way to say what it looks like is that it looks like this neighborhood in the web looks like the cone on the one skeleton of a tetrahedron. Okay. And in our story, foams can be non-orientable. So an important family, if I gave a different talk, I would talk about this a lot more. But just to keep in mind, non-orientable submanifolds, they behave a little differently than orientable submanifolds. So there's 2 basic interesting RP2s in the 4 sphere that I want to remind you of. So of course, the most natural way to think of the force sphere is that the traceless symmetric matrices of norm 1. How else would you think about it? And if you look at these guys, so they're traceless, so they have 3 eigenvalues, 2 with 1 side. Anyway, if they have, if I look at the matrices that have a positive root, a positive double root, or a negative double root, a positive double eigenvalue or negative double eigenvalue, that's a copy of RP2. Each of those is a copy of RP2. It's just determined by the line or the two-dimensional eigenspace, right? So there's 2 nice copies of RP2 inside there. So these can be part of our foams. The interesting thing, actually, the one little point I want to make about these things is, if you're a four-manifold topologist or topologist, it's important to understand if I had an orientable surface in the force sphere, its normal bundle's trivial. Okay? If I have a non-orientable surface, a little maybe counterintuitively, its normal bundle does not have to be trivial. Neither of these have trivial normal bundle, in fact. And their normal bundles have opposite self-intersection number, opposite Euler class in a natural way. So they're kind of important. So So we want to have a kind of functoriality property. So there's a kind of evident extension of the notion of a foam to a foam with boundary. There's kind of prototypical picture of some kind of foam. So one end there's just a simple theta web. At the other end there's a slightly more complicated thing. There's a tetrahedral point in here, then whenever I have such a cobordism, it induces a map between these 2 vector spaces. And the maps are obtained by counting solutions to the anti-self-dual Yang-Mills equations on this guy with some asymptotic behavior. And that's a lot of work, but I won't tell you about it.
You're still working in orbifold world?
It's all in the orbifold world, right? And, So again, I think of this. I see a picture like this. I make it into an orbifold, and I do orbifold gauge theory on it. So a little more generally, if I have a foam with some dots on it, that also induces each picture like this. No matter how I can put dots on the faces, I can sprinkle as many as I want. Those also induce maps. For the aficionados in the audience, whenever I pick a point on a face, I can construct a real line bundle over the moduli space and use that to cut down the moduli space. So, that's what I just said that. Great. But it just, there's pictures like this induce maps. So now we can rethink of some of the simplest examples. So we know, I mean, that it turns out the rank of J sharp of the unknot is actually 3. The representation variety is RP2. It turns out that there's no kind of cancellations when you do the floor homology. Its rank really is 3. But it's not now I can say something a little more interesting. There's these operators. There's so the empty cylinder induces the identity, but then if I put a point on it, it induces an operator called U. If I put 2 points on it, it turns out to be the square of this operator, U squared. So there's an action, actually, of the polynomial algebra on this so again, Z2 polynomial algebra on this generator U on this floor homology group. And anyway, the upshot is that as a module, it's just this simplest module it could be. So it looks like the action of the cohomology and the homology of RP2. So a similar analysis works for the theta web, but now the story's a little more interesting. For each edge, when I take the product, I can put a dot on the corresponding face. So I can put a dot on this kind of upper edge, on this face, or on this bottom face. Those induce, so I've called the edges E, F, and G, and then there's an operator UE, UF, and UG. You can check that they satisfy, these operators satisfy the relations in the cohomology of the flag manifold. So they satisfy these nice relations. And in fact, as a module, it looks like the homology acted on by the cohomology. So there's quite a bit more going on. And in fact, if you know Hovanov's SL3 homology story, this kind of looks like it, except that we're doing Z2 coefficients and we don't care so much about orientations and stuff. And then, so, then you can take his paper, steal all his ideas. Always a good thing to do. Steal, anyway. So this looks very much like that SL3 story. And a bunch of things, a bunch of the rules that are true for his story turn out to be true for our story. So here's this simplest example of that. So here's some foam. The foam has an extra component, which is a two-sphere, which I think of as just, it has to be a really standard unknotted two-sphere with two dots on it. And then I can just get rid of it. And it induces the same map. Okay? And so if the two-sphere has two dots on it, it induces the same map as just removing it. If it has any other number of dots, it just induces 0. Okay? A consequence of that is that there's a neck-cutting relation. So if I have, again, this is supposed to be a standard thing. I mean, this thing, this foam is some knotted surface. But if I see a bit where I can put a nice standard disk, unknotted disk in here, then I'm allowed to use that disk to cut it. I cut it like that, but then I have to put some dots, it turns out, to accomplish the cutting. So in other words, J, if I have some cobordism that includes this picture, I apply J to it, that map is equal to the sum of 3 maps. Okay? So we can do that. That's wonderful. Another thing that you can do is you can pair up tetrahedral points and get rid of them. And another relation is that if you have a bygone in your if you have a bygone, so there's this is in, unlike the other pictures, this is a story about webs. If I have this graph that has just this, there's a vertex and a pair of edges that appear and then disappear, then the J sharp, that should be J sharp of this guy is equal to J sharp, just 2 copies of J sharp. So the rank doubles under this operation. Actually, this cancellation of tetrahedral points leads rather quickly to what's called triangle relation. If I have a triangle in my graph, and I can just get rid of it. So that the fact that those 2 maps were the same is part of the proof of that. It's saying that composite of the obvious map from here to here and back is the identity. Right? You should put those in the other order.
These all embedded statements. After I graph, you have the triangle.
Yeah. Everything, there can't be any nodding. It has to really be an embedded statement. And the most complicated of the relations in Hovanov's story that you can prove is the square relation. So square relation says that if you have again, sort of flat square inside your graph, the J sharp of this guy is equal to the sum of these 2 guys. Okay, so a corollary of that is that if, for example, your graph is is bipartite. So bipartite means that you can divide the edges into two sets, and the vertices into two sets, and all the edges go between one set and the other. So if you have a bipartite planar graph, then in fact you can simplify it to trivial graph by using these three moves. In fact, so a little more generally, any graph that you can simplify using those three, so the bigone, triangle, and square move, you know that the Tate coloring satisfies the same rules, I should have said. So in this context, the number of Tate colorings is equal to the rank. So now I think if you're a graph theorist, maybe you can care about this a little bit. I finally said something that is, it's of course trivial to prove the Tate coloring thing for bipartite graphs, but this group is trying to be the number of Tate colorings in, not all graphs, but for a large chunk, we know that the conjecture is true. So and it actually has more properties. So there's a
the proof of the four-color problem for bipartite graphs, is that easy?
Yeah, it's easy. Then it has a Hamiltonian circuit, and if it has a Hamiltonian circuit, it's easy to see. Actually, just so if you have a it's easy. Yeah. Anyway, so there are more wonderful properties that it has. So if you have, so there are exact triangles that help you compute it. So suppose I have three webs which differ only in one three-ball, and so here's this three-ball, and there are these 4 points. These 4 points on the boundary two-sphere are always the same, and inside I have these three different bits of web. So here's a little more planary picture, but it's not quite planar because this guy isn't planar. So what I want to say is that these guys differ. There's a natural kind of elementary cobordism between these guys. And the next picture is meant to kind of indicate that. So the red and blue bits are two of the bits of web that were in there before. This yellow bit of surface, which is this kind of hyperbolic piece, and these two half disks. You're supposed to imagine that's the projection from the three-ball cross I into the three-ball of a surface, which has as its sort of elementary saddle cobordism, but then I have these two extra edges, so there's some extra disks. And this cobordism, in this case, has one tetrahedral point in it, by the way.
So this is a generalization of the exact triangle in harmonic homology?
Well, it's a generalization of the exact triangle in actually, it's a generalization of Floer's exact triangle, which is earlier. So, and it's about Floer homology. So, but there's a okay. Yeah. So the theorem is that actually these guys fit into a long exact sequence or exact triangle, and so that's helpful. And in fact, there's you can play some more games. So so here are essentially the same pictures that I had before, but now without the bar, extra bar. So these are just, they are what they are. So actually, these guys don't fit into an exact triangle. This is one little tricky point about the distinction between doing SO3 gauge theory and SU2 gauge theory. For SU2 gauge theory, there is an exact triangle for these guys, but when you're doing SO3 gauge theory with SO3 gauge group, one of these guys is the number of components of one of these guys is different. The number of components of one of these three guys is different from the other, number of components of the, the knot or link is different. And that means there's some extra stuff going with SO3 gauge theory. So anyway, but what happens is that there's an exact triangle that relates the guy with the bar to two of the guys without. That's the way the game turns out in this story. So each exact triangle involves an odd number, one or three webs that have where the topology of that piece is an H. That's the way the game works out. And of course, they fit into an octahedron. So here's the original. This is the actually original guy has a different twist here. That's why it's called L prime. And now let's see if that worked. These guys there are four exact triangles in this story. There they are. And it turns out, well, there are four other triangles. What do? They commute. Well, what else could they possibly do? And, this very sadly looks just like the octahedral axiom in triangulated categories. The kind of thing that makes me feel very sad, actually. But what can you do? There it is. This is explaining to you why it is an interesting thing, as far as I'm concerned. So I want to
That's one of the axioms that makes a triangulated category reasonable, so that the things you would usually do with like groups and subgroups
Sure.
still work.
Yeah. But it's cool. No, of course it's a good thing, and it comes up, in a natural geometric way in this context, right? It's just, what else could it do, right? I mean, anyway.
So you're not just getting triangles, you're getting a triangulated category. You should like that.
No, I don't like it. It makes me sad. Oh well. Anyway, but this actually connects in an interesting way. So I mentioned there are two characterizations of the Tate colorings, and actually there's a connection of the octahedron to this story. So Tut has had a nice characterization, and it's characterized by the fact that the number of Tate colorings. So this is all in the planar context. It's 3 if it's a circle, makes sense. 0 if there's a bridge. It's multiplicative for disjoint unions. And it satisfies what's called the Tut relation. So the Tut relation is the relation that if I look at these four guys, then the alternating sum is 0. Okay, so that's it. If you know that your invariant satisfies it, then it's counting the number of Tate colorings. So that's a conjecture then. And the these four groups that appear in the Tut conjecture are the belt of this octahedron. And in fact, you can check that, there's the belt of the octahedron. You can check that actually the composites, so the maps all go in the same direction, by the way, around this belt. And you can check that the composite of any two consecutive guys is 0. So these vector spaces give you a little four-periodic chain complex. Another thing you can check easily is the ranks of the homology of that chain complex at opposite edges are equal. And the Tut conjecture means that the homology at the adjacent edges is equal. Now, it might be. You might wonder, you always want to look for something a little stronger to prove and see if you can prove that more easily. So you might wonder if, in fact, that was a kind of strong Tut conjecture would be that actually that's an exact sequence. And that turns out to be false. In fact, when you try and apply that to the dodecahedron. So, and perfect timing. That's it.
J-sharp of that graph?
Did we compute J-sharp of that graph? Well, you know, compute privately, yes. I mean, you know, we did some pretty horrible stuff with actually just trying to understand. So, by the way, the representation variety of this guy is easy to compute, easy-ish. There are, you know, well, there are 60, sorry, well, yeah. There are 10 representations that correspond to the Tate colorings. So 10 conjugacy classes of representations corresponding to the Tate colorings, giving rise to 60, you know, rank 60. There are 2 irreducible representations. And in fact, you can kind of see them because this guy's that orbifold is a hyperbolic orbifold, and you can, you know, it turns out it has a cover that's like Thurston's very first example of interesting hyperbolic 3-manifold. And anyway, so if you look at the based representation variety, the picture you see is that there are 10 copies of this flag manifold. Those are the guys you like. And there are these 2 copies of SO3, which you don't like. They have to go away somehow when you pass the floor homology, when you compute things. And it, you know, so if you look at, so the cube, so this guy's actually nice in the sense that those are smooth. If you look at the cube, one skeleton of the cube, you can actually figure out, its representation variety is a mess, but you can perturb it. You can perturb it in a couple of ways. One way you can perturb it, it gives you, let me think, I think 4, yeah, it gives you 4 copies of the the flag manifold, and again 2 SO3s, and then you can actually perturb it a different way. So it gives you exactly 4 copies of the flag manifold. So that this kind of cancellation phenomenon that we want, we see in another example. And we've actually tried, you know, we have a sufficiently good picture that, you know, on a good day we believe we can get rid of these guys. But, you know, that would be a 50-page paper that nobody would ever read. So